So my name is Arjen Gašević. I'm a faculty member at Monash University in Australia. It's my really great pleasure to see so many people and so much energy going on around the conference last couple of days with many exciting workshops. And finally today we are starting with the main conference. Today's session has 3 presentations. The session is dedicated to new and foundational techniques in quantitative ethnography. I'm really excited to be chairing this session because some of the papers that I really wanted to read are all in this session as well. So I'm really very grateful to the conference organizers when they allocated me to this particular session. We have, as I mentioned, 3 talks. As you probably already know the drill, we'll have 10 minutes for each of the presentations. So these are technically generally short presentations. And then after that, we'll have about 25 minutes for discussion, given that we trim 5 minutes from the start of the session. So the first presentation is going to be given by David Williamson Schaefer, and it's about the mathematical foundations of epistemic network analysis. Many questions that I always had to ask about why certain things are and how they're organized in ENA, hopefully they will help us reveal today.
All right, well, thank you, Dragan. Just are folks able to see my PowerPoint? Great.
Yep.
So I actually, so first of all, I'm giving this paper on behalf of a cast of thousands, all of whom stepped back when we said, who wants to volunteer to present the paper? And I don't blame them. Presenting a math heavy paper at a conference like this is hard. I'm going to try and give sort of the highlights, but the paper really goes start to finish in an entirely mathematical description of what's happening with ENA. So if you're curious about that level of detail, I recommend the paper. I think it's quite good in that sense. One of the fundamental questions about ENA is actually a purely mathematical question, right? And it's, in its simplest terms, it's why did we make an entirely new network analytic tool instead of just using one of the hundreds of tools that already exist out there? And the answer is this, right? So here's 4 networks, right? Only one of these networks is the same as network A. I'm not going to waste your time by having you try and figure it out, but it's this one over here. If you want to be sure, you can just look at the connections between node 1 and node 7. And of course, what's happened is I've moved around the positions of the nodes of these networks, and that has created a visual artifact, right? Network A and network C look similar. And this is a problem because what it means is that unless there's some principled way of positioning the nodes, you actually can't rely on what you're seeing when you compare 2 networks to decide what the features of the networks are. Moreover, there's a ton of network summary statistics, which let you, over a whole group of networks, say which ones are similar and which ones are different. There's things like betweenness, centrality, link betweenness, closeness, degree, eigenvector centrality, link weightings, k-cores. There's a whole bunch of these, right? But all of these are structural. They're structural in the sense that they say that these, sorry, let me go back one slide. They're all structural, and all 4 of these networks have exactly the same summary statistics in terms of their structure. There is no way of distinguishing between these 4 networks in terms of betweenness, link betweenness, closeness, and so forth. Right? So the question is what we care about structure, or is what we care about content? And so the fundamental puzzle in ENA, right, is how to get summary statistics that compare differences in content. That is, that tell us which nodes are more strongly or weakly connected. And to illustrate this, I'm just going to show you I'm going to use a little bit of data for an illustration, and just so kind of the background makes sense. This is data from a study where residents, surgeons were using a simulation to perform a procedure. They collected data about how the surgeons were talking to one another and also what they were doing. It was coded. We did the 3-way validation. And the data that I'm actually showing you here, this talk, is not from this data. It's just illustrative. The codes actually are. So I'm doing a little bit of sleight of hand because, in fact, the details of the lines of data don't matter here. What does matter, right, is that we go through, in quantitative ethnography, we go through a kind of common process. We take the data, we code it, we validate those codes, although that's not what this talk is about. And then we look for places where within the same window of time, right, one code is connected to another one. And we record that in an adjacency matrix, and in a matrix that shows, in this case, that advice is connected to repair, right? As we go through the data, we start adding more connections in this matrix. So for example, further down in the data, there might be a connection between advice and trouble, and then another connection between advice and trouble. And there may be parts in the data, excuse me, where other things are connected. And we wind up with this adjacency matrix that shows us the structure of the connections within the data. Notice that I'm ignoring this part of the matrix because for our purposes in ENA, the matrix is symmetrical. That is, advice followed by repair is treated the same way as repair followed by advice. So we don't actually need this part of the matrix. We'll come back to that in a little bit. We call this matrix the omega matrix. And literally the omega matrix just says for any unit, the cells in that matrix are the strength of connection between code I and code J across the data for that unit. And the question that we have to ask is, how do we go from this matrix to a set of summary statistics that compare differences in content and a set of network visualizations that are co-registered with summary statistics? That is, we need a way of knowing which nodes are connected more or less strongly, not just what the structure of connection is, but which nodes are connected, and also a visualization that shows us which nodes are connected in some useful way. So the first thing that we do is construct adjacency vectors. For each of these adjacency matrices for each unit, we just unwrap the data in the matrix. So literally, we say, well, we don't need that data. Those first three numbers represent the connection between advice and repair, advice in a real case, advice in trouble, which are some of the codes that the surgeons are using. Then the next two numbers represent the connection between repair in a real case and repair in trouble. And this final number, right, is real case and trouble. And so we're just going to put that over here. In other words, we turn that adjacency matrix into a vector that represents exactly the same information. There's no information lost in this. It's just re-representing in a different format. And of course, we do that for all of the different people usually in the data. Now, there's one kind of tricky thing to think about here. If this is the matrix, right? Each of these lines of data is actually a vector in some high-dimensional space. That's what it means to say it's an adjacency vector. And there's kind of a critical question we have to ask, which is whether these two lines of data, right, or these two lines of data should be considered closer together. Right? I can make an argument that the blue ones should be closer together because the tips of the vectors are close together in the space. I could make an argument that the red ones should be closer together because the angle in the space of the red ones, right, this angle is closer than the angle between the red one and the one over here. And here's the thing to keep in mind, right? I can take a vector and multiply it by a scalar. I can just make it longer or shorter by multiplying everything by the same number. And what that means is the length of the vector is essentially proportional to how much someone is talking. Right? So if I don't care about the information about how much someone is talking, then what I actually want to do is make all the vectors be a similar length so I can compare the angles rather than comparing the distances. So that's actually what we do. We normalize the vectors to a unit circle, which just means we take this matrix and we divide every vector through by its length to create a normalized adjacency vector. Now this matrix still has all the information, right? We can still see that the top two people, right, make more connections between advice and trouble than the bottom two people, and the bottom two people make more connections between repair and a real case than the top two people. But that basically would make you crazy if you tried to interpret this huge matrix just by looking row by row, column by column, and figuring out who's ahead in which column. So what we do is a dimensional reduction. There's two different ways we do it. One of them is using a singular value decomposition. I'm not actually going to explain the math of a singular value decomposition. We'll take that as shared for now. But the basic idea is a singular value decomposition shows me the view into the space of vectors that gives me the most information. So for example, it would flip this table so that I can see the biggest spread of the data across the space. So we construct the singular value decomposition and rotate the data to produce a new matrix, which is basically the rotated matrix. In a special case where we have two groups that we're interested in seeing the difference between, we do a slightly different rotation, which is called a means rotation. The paper goes into plenty of detail about this, but basically we construct the vector between the two means of the groups in the high dimensional space, and then we use that to deflate the space and rotate. Again, the paper has more of that. The effect of the means rotation is to take a bunch of points like this, find their means, and then rotate the space so we get good distinguishing characteristics between the means. Now, whichever thing we use, the singular value decomposition or the means rotation, right? We're going to get a new set of vectors, which are the rotation of that original set. In an SVD, we get the first dimension of the SVD and the second dimension, which take up the first and second most amounts of variance, which we refer to as SVD1 or ENA1 and SVD2 or ENA2. If we do a means rotation, right, then we're going to get two dimensions, the first of which is this dimension that separates the means, and the second of which is the first SVD dimension. And this has the advantage, as I say, of giving us values for each unit that clearly distinguish the two groups, or as clearly as we possibly can. Okay, so I've showed you how we get summary statistics that compare differences in content. The next question, right, is going to be, how is it that I make sense of these dimensions? Right? What do those dimensions mean? They distinguish the groups, but what is it they mean? Well, the thing to remember is that we have this original matrix where these columns, the variables, are actually meaningful. And we can interpret a network graph for any given vector by looking at the values in the vector, and the biggest values have the thickest connections and smaller values have smaller connections and so on. So the question that we have to ask is, can we use this network to interpret the vector for this person? Can we use it? Can we construct a network diagram so that we can interpret these two things together? That is, can we construct a way so that this point is over on the right side because it has strong connections on the right, and it's towards the bottom because it has strong connections toward the bottom? This is called co-registration, by the way. And basically what we do is take the weighted average of the points. Again, paper goes into more detail here. And we construct the weighted average, which is equivalent to the centroid. We can do that on both axes. And the intuition is, if I have two nodes, each weighted 1, the centroid is going to be between them. If I have 3 nodes equally weighted, the centroid's in the middle. If I have one node that's weighted more than the others, the centroid moves towards that node. And now I can move, if I move the nodes, I can move the centroid to coincide with that plotted point from the summary statistics. Of course, I don't just have one plotted point, I have a whole bunch of plotted points. So we need to position the nodes so that, so that the plotted points and the nodes coincide. That's what gives us this co-registration. So how do we get the node positions? Well, we actually go back to the omega matrix and we compute the node weights from it, which is literally just the sum of each row of the matrix, now using the fact that the matrix is symmetrical. Right? And then we take those node weights and we find their average, basically, right? We put the weighted part in the weighted average. And now the centroid over here is just the weighted average of the x coordinate of the node times the weight of that unit for that node, and similarly across all the nodes. And that gives us the x position. Well, this, folks, is just a regression. It's a regression where the independent variables are the weights of the nodes across all the units, and the dependent variable is the actual plotted point value for the network. And now the betas are literally just give us the X location of each of the nodes that gives us the least difference between the codes and the nodes. Okay, so in summary, how do we go from this original matrix that we construct, and the construction of the matrix is in the paper, to these summary statistics and network visualizations? Well, we take the matrix and we vectorize it, then we normalize it, then we do an SVD or means rotation, and then we actually rotate using our rotation, and that gives us the summary statistics that we need. Then we compute the node weights, and we run a regression, and that gives us the node positions. And that's the math of ENA. And it's just a way of accomplishing these two goals in a mathematically rigorous fashion.
Great, thanks so much. Thanks so much, David. Yeah, appreciate it.
Yeah, my pleasure.
For a presentation, in a normal setting, we would have the flows. We'll have the opportunity to ask David some questions and comments, but I'll ask everybody to hold on that and just basically move on to the next talk, which will be given by Yeyu Wang, and it's about simplification of epistemic networks using parsimonious removal with interpretative alignment. So Yeyu, your time, 10 minutes, please.
Thank you, Dragon. And also thank you, David, for explaining the detail of the math in ENA, which set up pretty well for my presentation too. Well, hello, everybody. My name is Yeyu Wang, and I'm a second-year PhD student working with David. Today, I will talk about a method to simplify the structure of epistemic networks. In the mixed method studies, researchers apply qualitative and quantitative analysis. However, they're usually independent from each other. Quantitative ethnography combines these two approaches interdependently to understand culture, behavior, cognition, and some other human activities with thick description in a large scale. When we look at the QE model, if the qualitative interpretation is aligned with the quantitative interpretation, we think this model achieves the interpretive alignment. However, is the interpretive alignment the only criteria to define a good QE model? Probably not. There is another very important concept called model parsimony. Since QE has the nature of unification between the qualitative perspective and the quantitative perspective, involving fewer parameters achieve the same level of the explanatory power is considered to be parsimonious from the quantitative perspective. Also, from the ethnographic perspective, the model needs to capture the right amount of the detail to explain the phenomenon. Especially for ENA, we need to involve as few codes as possible, but still be able to tell the story. So this brings a challenge. Is my page moving? Okay. This brings a challenge to researchers in the field. You know, currently researchers conduct QE model refinement use a trial and error approach. So folks select one or more codes to remove, and then they check the deflated model to see whether the interpretive alignment is maintained. Since there is no principled way to do the model refinement, this process is usually very time consuming. To address this challenge, we propose the parsimonious removal with interpretive alignment, which is short for PREA, as our baby Yoda. To test out PREA, we first need an original model with interpretive alignment. So we picked the dataset collected by Zach Zwicky and his colleagues. This dataset was collected from a military training program. Participants collaborated as teams to identify and assess potential hostile vessels. We usually call those vessels as track as the term. There were two conditions tested in this study. Teams in the experimental condition had access to the decision-making support system, while the teams in the control condition only have the regular devices without that support system. So the discourse during the collaborative problem solving was recorded, transcribed, and coded by the 8 codes here with validation. Here is the original, here is the EN model with the interpretive alignment. First, we observe the interpretive alignment based on the code grounded in qualitative narratives and the node's position in the quantitative model. So in the discourse, we observe that the teams in the control conditions spend a lot of time seeking for the information of the tracks, while teams in the experimental group tend to make more technical decisions like issuing tutorial orders or making recommendations and so on. Quantitatively, if you look at this ENN model, you can see the seeking information locates on the most negative side of the first dimension, while those behaviors coding for the technical decision making locates on the most positive side of the first dimension, which indicates there is a great difference between the two types of the behaviors. Second, we observe the interpretive alignment based on the behavior of individuals and groups. From the qualitative perspective, we observe that the control teams had very different interactions compared to the experimental groups. And quantitatively, if you look at the plot and the confidence interval here, we observe a significant difference between the two conditions. Then we take the original model with 8 codes and generated 218 deflated models by having all possible codes combinations that could be removed. There are 6 examples of the deflated models that listed here. Then we correlate the node position of the reduced model with the original model to maintain the interpretation of the dimension. As you could see in this deflated model, the nodes in the deflated model moved a lot, like shifted a lot compared to the original model, which indicates the interpretation of the dimension on the deflated model is not successfully maintained. So we cross out this deflated model. Then we correlate the ENA scores of the reduced model with the original model to test whether the interpretation of the units are maintained. The deflated model has the ENA scores or the points located of the units shifts a lot as well compared to the original one, as you could see. The interpretation of the units is not maintained according to the deflated model. So we cross this one out. And then we look at the goodness of fit. The goal of calculating the goodness of fit is to ensure the interpretation from the EN model is reliable. So let's first look at how the goodness of fit was generated. We have the ENA scores for each unit derived from the dimension reduction technique as explained by David. In this plot, they are represented as the red dots here. And then the algorithm shifts the node positions around to find a good co-registration that the centroid for each unit is as close as possible to the ENA scores. In this plot is marked by the orange points. And we can see the ENA scores and the centroids are quite close to each other for the original model, which indicates this model has a high goodness of fit, a very reliable interpretation based on the model. But if we look at the deflated model, as you can see, that the EN scores and the centroid for each unit are very far away from each other, which indicates a low goodness of fit, which further indicates the interpretation of the deflated model is probably not reliable. So we remove this model from the deflated model as well. After step 2, 3, 4, we have 3 candidates model left. Then we started to confirm the interpretive alignment one by one. We start with the most parsimonious candidate model, which means it has the fewest codes left in the model. And this deflated model removed assessment, defensive order, and recommendation compared to the original model. We checked the qualitative and quantitative perspectives to see whether the interpretive alignment is maintained. I think my slide stuck again. Okay. We identified 2 teams. They work on the same training task and their decision-making process seemed to be the same. Except in team 2, there was a participant externalized their explicit assessment on the technical situation. And we coded that utterance as assessment as a code. However, the utterance of making explicit assessment is not important in the overall decision-making process. So let's look at the qualitative story together. For team 1, there is a F4 airplane detected, which didn't identify itself, which could be hostile, and the team updated the behavior of the track in their system, and eventually they issued the level 1 warning as deterring orders. For team 2, the process of issuing level 1 warning was the same. There was also a F4 airplane detected, which didn't identify itself, except in here on line 6, the track was explicitly assessed and assumed as hostile. So no matter with or without assessments, the two teams reached the same decision. So here we confirm that taking out the node of assessment doesn't change the qualitative story. And according to the quantitative confirmation, we can tell from the original model on the left that here is a significant difference between the two conditions. And for the reduced model, it's also maintained. The interpretive of the first dimension based on the node position also remained the same. As you can see, seeking information was still on the most negative side of the dimension, while the codes for technical decision making was still located on the positive side of the dimension. So the quantitative evidence also shows that removing the codes doesn't change the model or interpretation of it. So here is a final reduced model. This is the most parsimonious model with the interpretive alignment maintained. As conclusion, PREA method provides a principled way to refine the existing validated model. We also want to take a little bit of time to talk about the limitation of this study. So PREA cannot ultimately generate the optimal model from a large set of codes. It actually requires a validated code model to start with. And also, PREA was only tested on one dataset for this publication, but I collaborated with another collaborator who is Dr. Amanda Barony, and we submitted a paper to CSAL last year using PREA to simplify the theoretical construct of self-identity of the CREA development. And also in this study, PREA set the arbitrary threshold of 0.95 for our correlation criteria. The method to determine appropriate the threshold needs to be developed in the future. Finally, I want to thank all my co-authors for supporting and collaborating, and I would like to thank NSF, WARF, and the School of Education at UW-Madison for sponsoring this project. Thank you.
Thanks so much, Yayu, for the nice presentation. I think closes warranted, definitely. It's a really, really important talk as well. I have lots of thoughts and ideas, but we'll hold them off all for another 10 more minutes before we hear the final talk for today's session, which is the best paper nominee as well, by the way. And it's the talk that's gonna be given by Ayano Osaki. It's about socio-semantic network analysis of knowledge creation discourse on a real-time scale. So thanks very much for being here, Ayano, and look forward to your talk. Not sure.
Okay, thank you.
Good.
Can you hear me and can you see that?
All good. All good.
Oh,
yeah,
thank you.
You're good.
Okay. Hello, everyone. I'm happy to follow wonderful presentations. My name is Ayano Osaki, an assistant professor at AIIT, Tokyo, Japan. Today, I'm going to talk about a new analysis approach using sociosemantic network analysis, SSNA, and real-time scale data. The purpose of our study is describe idea improvement as a cultural context. Our research project have studied an analysis method for learning as knowledge creation. In this learning style, learners are expected to create and improve ideas rather than memorize a fixed set of knowledge. the combination of SSNA and in-depth dialogical discourse analysis is used to assess how learners engage to improve ideas. However, most SSNA studies have used older data, so there is a need to develop and examine methods that use data on a real-time scale. This study attempts to position the temporal analysis method for studying learning as knowledge creation by comparing the analysis results of older data and data that includes timestamp information. The SSNA is based on the social network analysis SNA method with an added semantic perspective. SNA is a method used to conduct network analysis on human behaviors by showing a person as a node and the relationship between persons as a link, such as the left figure. On the other hand, SSNA creates networks from keywords as a node and the relationship between keywords as a link in the right figure. Then we can see the transitions of contents in discourse by using SSNA. Moreover, SSNA calculates a score of degree centralities show how keywords densities in previous studies. In previous studies, total value of degree centralities has been used as a measurement of idea improvement. This slide shows a technique for our temporal analysis in this study. In these two figures are, in these two figures, we can see keywords in red circles, utterances, and the network of keywords. An analysis point is at the end of the tables. In the upper figure, the general SSNA shows only how the network structure develops from the first line to an analysis point at the end of the table, but not how the structure is restructured. In the bottom figure, SSNA combined with moving standard window method and the network lifetime restructures a network of keywords and interactions of utterances at an analysis point. The effectiveness of this SSNA, which incorporates temporality, was reported in a recent study, but the study dealt with older data that has no time information. Therefore, we examined approach using timestamp information. This study discussed two research questions. First, what insight can be gained from temporal analysis of discourse data with timestamp data compared to analysis without it? Second, can differences between high and low learning outcome groups be found by analyzing data on a real-time scale? The left table is a sample of ordered data. And the right table is sample of data with timestamp information. To answer the research questions, we conducted analyses that used collaborative discourse data. The data was collected in the regular biology class of 10th grade. Students discussed the human immune system in the class. I'd like to show the results of two approaches. The vertical axes show total degree centralities. The horizontal axes signify the order of utterances in the upper figure and time in the bottom figure. The comparison of these two figures results that analyzing ordered data did not correctly illustrate learning activities. The 4 arrows show the gap between the ordered data and data with timestamp information. Let's take the low 1 and the high 1 arrows as examples. In the upper figure, both utterances were shown almost simultaneously. However, these utterances are actually spoken at different time in the bottom figure. After the comparison, we analyzed the discourse data and confirmed a high learning outcome group developed constructive ideas. Finally, we are moving on to the discussions. The study had 2 research questions. The answer for the first research question was that learners created new and revised existing ideas, whereas at other times they maintained existing ideas. By employing data that contains timestamp information, we could see when learners created or changed ideas intensively. The second research questions required the idea improvement process pattern to be compared between the high and low learning outcome groups. The present findings confirmed that the peaks of idea improvement in the high learning outcome group were more frequent and longer than in the low learning outcome group. This is because timestamp information is a common indicator for multiple groups. Using data on a real-time scale allowed comparison of the groups of the same scale. Of course, this study has a limitation. We analyzed only 2 groups. However, this study confirmed the possibility of analyzing data using timestamp information. I'd like to close my presentation. Thank you so much for listening.
Thanks so much, Ayana. Also, applause is definitely warranted for your talk. It's really interesting. So look, we have about 18 minutes left for our discussion. So we had 3 interesting papers. 2 were more focused on ENA. The third one, which I really liked, was a bit of variety. It's also nice to see that we are seeing some additional methods in quantitative ethnography, and so that we basically can say that QE is not ENA. I mean, ENA is an important technique, but there are new techniques that will come, and we will see hopefully more and more of these techniques. And so this session obviously kind of focused much more on this quant part, but which is really an important part. But obviously this quant part could not possibly work without the qual part and the ways how this data are collected and how we are basically approaching the overall quantitative ethnography. But so to me, this was really interesting. I always wanted to see some of the mathematical formulas behind ENA, which really was exceptionally helpful for me and for at least us who come more from computer science, so that we can know how we can replicate, how we can re-implement ENA in another context or with another toolkit and start optimizing potentially some of these things. Yair's work is exceptional in such way that I'm seeing the importance of that. We often have a number of codes that are basically potentially polluting, quote unquote, some of our models, or some of the kind of networks that become really complex as well for interpretation. And therefore, we need to really kind of think about the ways how we can do that. Obviously, Hannah's work is really interesting because it focuses on the temporal dimension of the understanding of the ways how certain dynamics happen in a particular group, which is really an important lens that we can see in quantitative ethnography. I can keep summarizing and talking about my excitement about some of these works and ideas, but I'd rather basically let the group here to ask any questions that they may have or any ideas that may have with respect to some of the work that they had, their clarification questions, or questions, what would happen if I were to apply that work, or what would happen if I'm going to do something with that. So any questions? Anybody?
Am I allowed to ask a question of one of the other presenters? Is that fair?
Yes, it is. Absolutely.
Right. So Ayano and June, first of all, I love that paper, and I can see why it got nominated as best paper. I'm curious as to the kind of the notion of network lifetime. I'm wondering where the idea came from. How come you chose to implement that, right? Because you don't necessarily have to. I have to think about that sort of dropping off the old information. So I'm just really curious to hear a little bit more about how that came about and what you're thinking about using it with.
So do you have any comments, Anna?
If you have any comment, John, you can answer that.
Okay. I think one of the practical reasons for implementing a lifetime of the discourse is that we're usually analyzing the face-to-face discourse. So in a short period of time, for instance, in this case, we're analyzing the 40 or 45 minutes of the students' discourse within a small group. So in that situation, usually people are not going to remember everything. And the topics of the discourse is changing from the one time to the another. So we like to catch up, how many, for instance, topics they're discussing about, and also how long it takes during the one discuss topic. So that's why we implemented a real-time scale as well. And also, before implementing the standard Windows writing method, we didn't have any kind of tools for us to analyze appropriate size of the unit, like 3 or 4 conversation towns that are based on the dialogism. Maybe the minimum size of the analysis is going to be a 2 or 3. In this case, I guess 3. It's two sides. So which means that any specific point of the conversation town is going to be influenced by the previous one. So that's kind of analysis you implemented in the ENA. We use the technique, and also we implemented lifetime of the kind of chunk of the discourse is going to be alive within a specific time. Then we just assumed diminished sometime, then go to the next one. So that's why we implemented lifetime. And also, we just read the topic by it's bound BUST, right? The BUST, the concept proposed by complex network analysis scientist the Barabashi, and the BUST is a very interesting phenomenon for us to see. Usually people are having collectively or naturally increase the peak of the ideas, or maybe some transactions as well. So yeah, we love to see the phenomena like that during the discourse of the students.
Yeah. Part of the reason that I think that I zoomed in on that piece is, the temporal thing I thought about before, but the thing that I particularly like about that network lifetime is people have been interested in trajectories for a long time in ENA and in other places, right? Learning trajectories. And every time we've done them, and I'm looking at some of the people here that I know have done trajectory models, right? We do, okay, what's the trajectory on, what does the network look like on day 1 and on day 2 and on day 3? And then we draw lines between them so that we can see like how the trajectory unfolded, but it's completely discrete. The network lifetime actually makes it possible to construct a continuous trajectory model, which is something that I think ultimately is kind of what people have been reaching for, but we haven't had the way to implement it mathematically, and that solves that problem. So I think that's really cool.
Yeah, but because we're just focused on the structure of the network, that's why we can do that. But as you said, if you're going to use this kind of technique or algorithm by doing some ENA analysis, it's going to be a huge, you need a huge CPU power to visualize the network change, I guess. So,
I don't think so. I mean, Dragon can answer that question better than I can. But
right. So I love to see that.
Yeah, I think it's actually not going to be that hard. Well, okay, come back to the next conference and let's see if we've solved the problem. I mean, I think this is really cool.
Okay, and seems the time.
Looks like Dragon might have
I think
froze.
Dragon may have frozen, yeah. Brendan, maybe you could just take over and substitute and encourage people to ask some questions while we're waiting for Dragon.
I even had a question. It's hard for me to actually focus on mine because I want to keep going. All of these are such good topics, but Dragon actually said something that made me think of Yeyu's work. In some ways, I've thought about networks in a totally different way. He used the phrase of like, you could have nodes polluting your network space. And one of the things I was kind of curious about, if Yeyu or anybody else has thought about this, if you have an interpretive alignment that you like, it looks like we have Dragon back now. Maybe he's unfrozen. But if you have an interpretive alignment that you like, and then you strip stuff out, that's one thing. But it also, the metaphor that Dragon used made me think about, if you have a dominant node, like let's say you strip out all these other things, you could have a dominant node that washes out or might mask other patterns of connections that you look at. And I think the Priya model lets you get a grip from one end, and it's a super important one. But that one metaphor triggered this other piece to me, is like, one extension of it could potentially be, how do you think about taking out dominant nodes and seeing and still finding other stories or patterns that are you'd think are interesting. I don't know if you have thought about that at all, or how you see that potentially relating to Priya, but both your presentation and the paper and Dragon's comment kind of triggered that for me.
Yeah, definitely. I have been thinking about that, but that was already published by Dragon in ICQE 2019. So I remember that paper was about understanding the social presence and cognitive presence in the community of inquiry. And here are some dominant nodes in the network. And because of those dominant nodes, we cannot see any other pattern underlying that was buried by the dominant nodes. So the way that Dragon deal with that was taking out the dominant nodes, so the underlying structure was popping up. I hope that was a fair summary for Dragon's paper, but that one definitely inspired my work as well. So a big thank you to Dragon too.
Well, yeah, no thanks, but you went farther than us. We just basically did some initial experimentation, what could happen, but you really proposed a proper method, unlike us. So yeah, I think the kudos go more to your work, and it's really good. I'd really like to see how we can do these type of things more methodologically, as you are trying to do. To me, that's really what I'm seeing to do. I mean, what we were trying to do to scratch the surface, but I think it's really essential that you're kind of going through that process by far more methodologically, so that you can measure the steps on the way. So the point of either removal or any other aspect of the kind of finding most parsimonious model is really kind of that is helping us to have that kind of quantitative measure of the reasons, or that can help you justify why you're actually seeing the improvement in that model and its quality. So that really is exciting. Any other questions or follow-ups on some of these discussions that we had? Anybody wants to step in?
I have a question, but it's not theoretical. I wanted to ask you, how did you generate all of models?
Yeah, no problem. So are you talking about the deflated model, the 218 deflated model?
Yes.
Mm-hmm. Yep. So we have the original model with 8 codes. And then we could try to take out different number of codes, and the remaining will form a new ENA model. So you think about, you have 8 codes, and you can take out 1 out of 8, and then 2 out of 8, 3 out of 8, all the way to 5 out of 8. Then you cannot remove anymore because you need at least 3 codes in order to form an ENA network. So yeah, that's how we generated 218 deflated model.
And did you use the web tool for that, or how did it? Because when you were comparing in your presentation, you were looking at the structure like visually, right? So did you generate all of these models and you looked at all of them visually to make the first step in the decision process?
Yeah, during the process, we have several steps comparing the correlation between the node position of the node position and ENA score and goodness of fit between the reduced model and the original model. So that step was not visualized because that's a lot of computation. I only tested on 8 codes, but if we have more than 8 or more than 10, that will definitely be a big, like a heavy work if we want to do the visualization every single time. So the way that we address that is we just do the calculation at the very beginning. Feels like we're utilizing the power of the machine and try to minimize the human effort during the process. And after we shrink the scope to the candidates model that all have high correlations, and then we can manually or involve our human power, the efforts to check each model visually. So that's where the visualization kicked in.
It seems to me like Yao's work is quite interesting because it's kind of like a type of the stepwise regression analysis for using the ENA.
Yeah, absolutely.
So it's kind of backward and forward stepwise, adding one more code, or maybe to delete one more code in addition. So it's quite systematic and quite reasonable Parsimony model. So and also, I guess it might be easier for us to implement that into our code of the ENA because it's most of the algorithm is the same, but you can just delete it and such, then compare the best fits into the model. So it's very
Yayu actually has our code to do that. We haven't released the package yet, but she built the measurement that compares the interpretive alignment of 2 models, and then also basically the PRIA that removes it. Yayu, could you say a little bit about about the limitation that it has to be a model that is already validated? Like, because in stepwise regression, you don't really do that. You just kind of add things or take things out. Can you just say a little bit about why we don't take that approach, or you didn't take that approach?
Yeah, so from my understanding, please feel free to add more, David, if you want to add more. So from my understanding, we started with a model that already achieved interpretive alignment, and the model parsimony is just one more step to make our model more clear or easy or straightforward in order to interpret it. And if there is no premise of the interpretive alignment, the model at the very beginning would be a problem in terms of the validity issue, in terms of interpreting the ENA model at the first place. And also all of the procedures in the PRIA, we always compare back to the original model. That's requires us to make sure that the original model has the interpretive alignment at the very beginning. So the procedure of correlating the node position and the ENA scores back to the original model makes sense in that case. Otherwise, the procedure doesn't make sense. Do you have anything else to add, David?
No, that was basically perfect. I mean, we started with the stepwise regression And the issue that Yeyu was just saying made us pause and think, well, it's not exactly like stepwise regression because there's this kind of additional requirement of a gold standard model, which doesn't really exist in the pure stepwise framework.
Yeah. Yeah, sounds good. All right, so we have 1 more minute to have any other question or point that you would like to make. If no questions, David, do you see any further work on this mathematical model that you had for ENA? I mean, and also, like, I really appreciate the paper. Was that your intention as well with this paper to just really kind of fill this kind of space that we didn't really have the formally published paper that kind of outlines the foundations of ENA? And I guess that paper is almost like a further call for action, right? Any kind of further papers that are advancing ENA should be also offering something that is built upon this mathematical foundation. Yeah,
I mean, it doesn't have to be built on that mathematical foundation. It came about because people like you, computer scientists and engineers, were always saying, look, you're explaining what it is you're doing, or you're showing me the code. Can you just show me the math? So we wrote up the math to make sure the math was right. But yeah, I mean, I think as people are starting to do things like PRIA and DENA, directed ENA, and multimodal ENA, I think it's good to actually try and express those ideas both conceptually, or not both, conceptually and in the computer code, and actually provide the sort of clear mathematical descriptions so that people have multiple points of entry. I have no idea whether we'll achieve that goal, but I mean, that seems like something that the community should aspire to ultimately. And I will say though, it took us so much, David. 18 months of arguing back and forth about the notation and what was going on. So it was a non-trivial task.
Yeah, it's going to be a big challenge.
I completely appreciate it.
You can just leave that for your graduate students. You don't have to do that.
Right. Fair enough.
Yeah.
So should we?
But that's
the
key thing, is because I mean, you are really assigned this. Yeah, no, let's go before we go. But I think that's an important step because you are really kind of defining the formal semantics of your model with the kind of work that you are doing, which is really essential. And each of these steps in the way can have a completely different semantics in terms of the mathematical interpretation that you can derive from it. So that's why it's so important to have something.
Well, if you saw, there's a poster by Mariah Knowles that basically who took a look at that math more or less and said, well, why not just do rotation by an arbitrary regression? And right, so now you can get continuous variables where there's a mean rotation. And what she did is essentially say, well, now I can put a control variable on, and I can make both the x-axis and the y-axis meaningful, because you can just drop in one spot in the math a different piece of math, and everything else sort of coheres around it. So I think it's been very valuable in that regard.